Okay, Assalamualaikum and good afternoon, everyone. So, first of all, let me introduce myself. I'm Dr. Hishamuddin, and you can call me Dr. Hisham. Okay, good afternoon, Dylan. Uh, I'll be teaching you the mathematical methods in physics for the second group. There is another group which is taught Dr. Nizam, and Dr. Nizam is the essentially the boss of this particular course. Okay, so I'm just aiding Dr. Nizam to teach the second group. Okay, let me start by saying a few preliminary things. One of the things is the book that I'm using. In fact, both of us are using the same book. Both of us, Dr. Nizam and I. We are using Mary Boas methods in physical science. Can you see this?
Yes.
Okay. So this book is good to have, so you can buy it if you want to keep it for your future reference, and but you can also try to get it elsewhere if you want. Okay. The other thing that there are other books also on mathematical methods. One that I would also recommend would be Riley. Okay, but again, since we are sharing the course, I'm going to just focus on Boas. So the other preliminary thing is perhaps is the course assessment. So there will be this is according to Dr. Nizam. There will be quizzes, assignments, and for my own self, in the assignment, for example, I will have a particular module that allows you to be exposed to some kind of research topic or research journal paper, so that you can have a look and see how it relates to the course that you are taking. Okay, so that will sort it out probably later in the course. Okay, so there will be test 1 and test 2, 15% each. So these are normally in week 5 and week 10. Okay, and then you have the final exam, which is essentially 40%. So all of those make up 100%. So I might have a slightly different way of distributing the marks. As I said, I might have this SCL module for you to look at instead of just assignments. Okay, so okay, let's start. Okay, now one of the things, why do we have to learn mathematical methods in physics is perhaps physics for most, in fact, if you compare all the different sciences, physics is probably the most closest to mathematics, because you can see all the analysis being done through the language of mathematics. So a physicist is expected to know an arsenal of mathematical tools. Okay, so in other words, given if suppose the a, a, a student of physics are given a particular problem, they are expected to know certain mathematical tools to analyze the problem. Okay, so this particular course is actually this first course. Okay, this first course is actually half of the book on Boas. Okay, the second half, the more complicated half, is in the old curriculum is taught as mathematical physics, which is the second course. Okay, in the new curriculum, which is starting this semester, they are just maths method 1, maths method 2, but no, you don't need to worry about those. Okay, But there is a mathematical physics too, mathematical physics, which is the second course of this particular course. Okay. So, all right. So the first chapter, if you look at the chapter of the book, let me just go through Boas for a while. You can see the book, right? Okay, let me just go through the table of contents. So this is going to be, if you look at the table of content, it might scare you a little bit, but no, again, this is one of the courses that you are taught almost everything, but no, the main point is that you be able to use those to no, to solve physics problems. So you have the first chapter being series, and then followed by complex numbers, linear algebra for the third chapter, partial differentiation. Some of these things you already learned in high school, so some of it we can go through faster, I suppose. And then you have multiple integrals. Okay, again, some of it the high school stuff, vector analysis, and then you have Fourier series and transforms, and of course the final chapter that we're going to touch upon in this particular course is ordinary differential equations. So 8 chapters altogether. So you might sound scary, but again, some of the chapters are things that you have already seen in high schools, okay, or matriculation or STPM. Right, let me go to the notes then. So the first chapter of the book is essentially on infinite series. So essentially, what is a series? Series is essentially, okay, let me talk about the sequence first. You can formulate a sequence of numbers. Okay? So this can be done by, you can do something like, so I can have something like the Fibonacci sequence. Begin with 1, and then there's nothing added to 1 gives you another 1, and then 1 added to 1 gives you 2. So these are numbers that arise in a Fibonacci sequence, for example. So you can have a set of numbers, a series of numbers that sequence of numbers that gives you this Fibonacci sequence. Okay, and Fibonacci sequence, you can actually see, if you Google this up, this appears in Nature. Okay. What about series? Series is in our part in the language that we're going to use is essentially the sum of those sequences. Okay. So the series, you might think of this as a series, but no, this will be a sequence rather. So you look at the individual numbers, but the series will be a sum. Okay. Now, why is series important? To start with, probably there are 2 ways of looking at it. I call it 2 modes of thought. Okay, again, these are not really in the Boas book. It's just something that I've been thinking about, the idea of how to motivate this particular topic. There are 2 modes of thought. You either think of it as a physical thing. Okay, that means what do? You want to get numbers out in a sequence. What you can try to do is try to sample a physical data at discrete points. Okay, so you can look at, say, a number of population of rabbits, for example, at one point in time and then another point in time, and so on and so forth. So then you get sequence of numbers. Okay, and usually what happens in those cases, we sample physical data at discrete points so that you can actually do some analysis, and then you can actually predict events and quantities. Okay, so that's what we often try to do. In a mathematical mode sense, why do series become important is because you can represent some mathematical object or mathematical process using a simpler mathematical operations. Okay. So what are the simple mathematical operations? They are simply just the addition and multiplication. Okay. And this you can see it happens in when you try to do a discrete version of integration, okay, or discrete version of some more complicated mathematical operation. So all of this involve the idea of series. Okay? So let's just have a look at this example, which is probably something from biology, but it will relate to something that you should know by now. It's very important in our current situation. So this is a sequence, for example, of a bacterial growth. Okay, so how does a bacteria grow? It splits up the cell into two, and then it skips one cell goes to two, and two goes to four, and four goes to what? 8, right? So that is 2 to the power n, essentially. Is that right? 2 power 1, 2 squared, and 2 cubed. Okay, and this is precisely is the what we call, let me go to the website. Are you seeing the website here? Anyone? Great, okay. Please do respond because I'm not sure whether I can't see you all, okay? Because with my full screen mode here. Okay, here is, now you probably have heard about R naught, right? Anyone over here doesn't know what R naught is at this time? Huh? Yes? Where do you hear about R naught? Hello?
There's some of, hello, doctor.
Yeah?
Interrupt you, but there are some few students that can enter the class.
Okay, all right, okay. It should be automatic, but okay, thank you for reminding. Uh, all right. So R naught is the what they call reproduction number. So if we look at the Wikipedia page, so this is R naught that you have heard in the COVID-19 pandemic. No, every day there was a public announcement what is R naught for today or something like that. Okay, so it's the basic, what we call the basic reproduction number. And the case of the cell division growth is essentially the case of the reproduction number of Ebola. Okay, Ebola is a very scary disease. Okay, and it has this ability to spread very quickly, but it also has this one complication with respect to using R naught is that no, there are other factors coming in, things like fatality rate. So people die from this disease easily. So with that fatality, usually those diseases with high R naught tends to be very fatal. So and when it's very fatal, it short circuit the expansion, so to speak. Okay. COVID-19 is probably something in between, I suppose. I'm not sure what the average R naught for the global case, but you can try to play this game of trying to predict. Okay, but there's also other factors coming in. Okay, so that you know to go into all this modeling stuff, then you probably need a little bit more care about the the whole situation, what is involved, what factors are coming in. Okay, but these are just essentially sequences and series. Okay, so going back to this. Okay, so in other words, over here, this cell division, as you can see, also the same thing with the reproduction number of the Ebola disease. There is another thing that you probably have seen this before, is the idea of nuclear fission. Okay, I can't remember the exact nuclear sequence that's involved, but it involves, say, the uranium nucleus. Okay, this should be the 235, I suppose, or 238, I'm not sure. Okay, and then you add, you bombard this nucleus with, say, the alpha particle, and then you get something in the end. I can't remember what it is. You can look it up. So you get this chain reaction thing. Okay, so this again, you can play around with sequences and series. Okay, here's another nice example. Is sometimes what people do to analyze some mechanical system, what people do is they do all this snapshot photography, and then they can start to, okay, with this particular ball, for example, I can actually see, once it bounces off, it goes to a certain fraction of height of the initial height, and then it goes to a certain horizontal distance. So you can start to, okay, I can start to analyze this by just looking at the distance of the height, okay, and how it drops, and then how it translates. Okay, so in this case, this, I think, is, I was trying to guess what's the horizontal distance is about 2/5 of the height, and then after each bounce is about 5.57 of the original height. Okay, so you can start to get numbers of the falling height, for example. Okay. So you get here 507 h. H is the original height, and then this will be again multiplied by another 507, that gives you the 25/49, and so on and so forth. And then you also want the horizontal distance. So the horizontal distance, you have to remember there are, so okay, you have this height here, but then you have two of this, it's symmetric about that point. So you have this factor of 2 coming in, and then it multiplies the, what's the factor over here? It's 2/5. Okay, 2/5 of the height. Okay, and then times by 2 because of that symmetric distance there. Okay, so you'll be able to predict the horizontal distance of the bouncing ball, how far it travels. Okay, so you can do this kind of sum, and here you don't need any equation of physics at all. Usually what one needs is probably, you have to solve quite difficult F equals ma kind of equation to this bouncing ball, but here you don't need to. Okay, you just need to know how far it drops in terms of height and how far it travels in terms of horizontal distance. Okay, so here it's given by this series, so now it's being summed. Okay, it's being summed, and then you know how to sum this. Okay, this is essentially what we call a geometric progression. Okay, so you have say the beginning number in the sequence, say A, and then the following number will be followed by a factor of R, and then multiply again by R for the consecutive number, so you get AR squared and so on and so forth. And for the series, you just sum this up. So this is what we call a geometric series. Okay, and you probably have seen this in terms of a formula before. Okay, you can actually do a partial sum. That means you, instead of making this the series goes to infinity or the sequence goes to infinity, you just take a partial sum. So here you stop at particular n, okay, and denote this as s subscript n. And to get the whole series, then you need to take the limit of this n goes to infinity. Okay, so here there are two things. One is the series itself, and then the other is the limiting what you call operation. So such a series, because n goes to infinity, this is called an infinite series, and one has to find out whether the number that you have over here is going to be a finite number or a infinite, or it does something else, could do something else. Okay, so this is an infinite series, and one needs to check whether this is actually convergent. So if it's convergent, then your s is a finite number, finite I, finite s. Or if it's divergent, then it's what we call modulus s is going to be goes to infinity. Okay, but let me just remind you, this is from high school. The formula for the partial sum, you already know what it is, as n is equals to the initial term a times 1 minus r to the n divided by 1 minus r. I hope everyone knows or still remember this, right? Anyone? I hope I'm not talking alone. It'll be 2 hours of this. Oh, okay. Sorry. Please do remind me, okay, if you're getting in. I have auto admit on, but it doesn't work when I have a different screen on. No, I have to go to this particular screen. But let me know if anyone is actually wants to come in. Right. So one of the things that we do is to take the limit then. Okay, so when you take the limit, the convergent case is when r is the modulus of r is actually less than 1, and then you can actually show that your limiting sum is going to be equals to a over 1 minus r. By the way, you should be able to prove this, and I give you a hint how to do this. Now, for this geometric series, how do we know it's convergent or not? There is proof of this, okay? But let me just mention the results rather than the proof. Okay, the proof is in the notes. You can have a look. So as I said, for the case of r, the modulus r less than 1, which means r is between -1 and 1, okay, it's convergent. Okay, that means the limiting sum will be a finite number. Okay, when r is greater than 1, then it's going to be convergent. Okay, somebody coming in. Right. And then when 1 is also divergent, as you can actually easily prove. Okay. And then finally, when r is less than -1, okay, it also diverges. Okay, that is r less than -1. Now there is another odd case when r equals to -1. And this is the case where I mentioned just now that besides being divergent or convergent, there can be something like this where your sequence is actually oscillating and the series does not converge at all. Okay, because it goes from 1 minus 1 and 1 minus 1, and then you either sum, if there are n, even n of that, they will become 0, then if it's odd, it becomes 1. So it doesn't really converge. So now we can use this geometric series to solve, say, the case of the bouncing ball. Okay. So what do we have? We have that beginning factor pull out 2 to the 5th, and then 5 to the 7 is the 2 to the 5th is essentially the I think how much the horizontal distance is, okay, and then 5 to the 7 is the factor r, okay. So you can do, again, I'm not going to go to the details because this is supposed to be high school stuff. So you can do all the geometric series inside here, and you essentially got your how far is the bouncing ball is going to travel horizontally. Okay. Right. Another interesting application of geometric series is essentially the decimal representation of fractions. You probably recognize the fact that, okay, if you have numbers like 0.6666, no, and it goes on forever, this is essentially the number 2/3, right? So it's a finite number, okay? But if you look at 0.66 and so on, okay, you can think of it as a geometric series in this sense. You have 0.6 is 6 over 10, and 0.06 is 6 over 100, and 0.006 is 6 over 1,000. So you can see that going from one term to the other, you have a factor of 1 over 10. So your r essentially 1 over 10, and the initial number in the sequence is 6 over 10. So you can actually do, okay, the geometric series sum, and of course what you're going to get when you take the infinite limit, so you get this to be a partial sum, okay, Sn here. So it will be 2/3 times 1 minus 1 over 10 to the n. But as you take n goes to infinity with the 10 to the n on the denominator, this will goes to 0. Okay, so you finally get to the what you call the known result of your number here is really 2/3. Okay, and you can, okay, this is boring stuff, I suppose, but now you can do something else. You can take a less obvious example of a repeating decimal number. Here's 1, okay, so you have a 0.9, and then it goes into some other bunch of numbers, 285714, and it repeats 285714, 285714. Okay, and you can use the same technique to represent, okay, I'm going to bring out that 0.9 out, okay, but now I'm going to add this with this 0.02857114, which repeats. Okay, so this part you can look at as a geometric series. Okay, and what happens in this particular case, yeah, you can look into the details later on. You will see that this number that has this repeated sequence of decimal numbers, okay, is also a fraction. Okay, so in fact this is a very deep result in arithmetic, sorry, in arithmetic, that if you have a decimal okay, a decimal point with repeated numbers, then you know it's going to be a fraction. So any fraction for that matter, then you can represent it in terms of some repeated numbers of your decimal points. Okay. So the deep result is this: your fractions, either you represent it decimally by a terminating decimal. Of course, you have to include cases like 0.5, which is equal to half. Okay, so this is it terminates at 5 here. Okay, or you have your repeating this decimal. Okay, so in other words, there's a class of numbers in the real numbers, okay, for which when it repeats, you know that it belongs to the rational numbers. Okay, so that's it's a nice result, and it actually also works on different number bases if you want. Okay, so let's go to the a much more general theory. So the geometric series, we have used it as a prototype of infinite series. Okay, so a more general series is what we call arithmetic series. Okay, and oh no, sorry, I'm talking about another special type. This is arithmetic series. Arithmetic series is another series that you have learned in high school. So I'm not going to go through this. Okay, but the general series. Okay, let me go to the general series. Okay, here are other examples of series. Okay, you can see over here it doesn't fall into either the geometric case or the arithmetic case. Not geometric series or arithmetic series. But what's common behind all these different series over here? The common thing is the fact that each term is labeled by what you call your natural numbers. Okay, so you can talk about this as an arithmetic series. I should say this. Should I differentiate between these two? This one should be called arithmetic progression rather. Okay. But never mind, we call this as a general series. So this general series are going to be labeled by some integer labels. Okay, so this the terms are labeled integer wise. Okay, in fact, one can do even much more general than this. Here is already a general thing. Here you are not dealing with numbers, but you are dealing with variables when you put it in as a particular series. Okay, so generally a series might just look something very very weak like this, where you have a kind of function or no a term that is labeled by 0, 1, 2, 3, and so on. Okay, so that will be a how the general series would look like. But of course, when you label it this way, there must be a reason why you label this as F1, why you label this as F2. So usually these are going to be formulated as a formula, and you'll be able to see the series explicitly. Okay, so generally we are interested in the sum, for example, and here are some cases. Okay, here's a sum of n cubed. Okay, sum of n over 3 to the power of n, and all of these are sum from a beginning number. Say here is actually n equals to 1, and it goes all the way to infinity. And one of the thing that we want to know is whether it's convergent or it's divergent or no, oscillatory. Okay, so these are going to be of our interest. How are we going to test this particular thing? One of the things that if you remember, okay, we didn't quite do the proof just now, but I just asked you to do it. The case of the geometric series. Let me go back. Yeah, the case of a geometric series, I ask you to write out your partial sum as n, and then I ask you to write out your partial sum as n times the factor of r. So you can actually see the difference between the two series, and you can actually try to sum them, and then you'll be able to get the expression of the geometric series. Okay, that technique, one has to be very careful. That technique works okay for what we call a convergent series, but when you try to do this for divergence, for am I still online? Because let me just check. Because this morning's lecture, no, the connection failed twice. Okay, let's look at this divergence series. So here we know that, okay, we're going to sum these numbers which are all greater than 1, okay, infinite number of times. And of course, you know that this is supposed to be infinite. It's going to be divergent. But if we try to do something like what we have seen earlier, somebody coming in, we try to do something like this. We double your series over here. We just multiply by 2, and you can see what happens over here. You get the same numbers apart from that first number in the first series. So if I try to do something like this, then I can say, okay, your 2 times s is going to be just s, this s, minus 1, minus this first term. But what would that imply? Well, if you just write out what it is, 2s equals to s minus 1, and then you rearrange it, and then you get your s equals to minus 1. And of course, that is nonsensical, okay? So you know that, okay, in this particular case, what we are trying to do, we are adding two different, we are doing operations with two different divergent series. So you cannot actually do that, okay? Right. Okay. Now let's look at some examples for which we can actually try to see how do you do the limits and so on and so forth. Okay. So in order for you to find out whether a series is divergent, or it's important to know how the sequence actually what's the limiting term in the sequence, for example. Okay, so here's a complicated sequence over here. There's even is a fraction, of course, with powers of n on top and bottom, and even a square root at the bottom. So what do we do? Well, in this particular case, one normally, the first attempt that one should do is try to divide top and bottom by the highest power from the numerator, or actually you can do it for the other case as well. So here is from the numerator, so it's n cubed over here. Okay, so I divide top and bottom by n cubed. Okay, and then I will find that okay, the powers which are smaller than the cubic power will get numbers like this. Okay. Also over here, one has to be careful also about the square root, but no, this should be okay because when you take n cubed inside the square root, this is actually n to 6. Okay, so this get 1 over here, for example. So when you take the limit n goes to infinity over here, then you'll find that okay, this goes to 0, this goes to 0, and the rest stays. And essentially the limiting number of the sequence is going to be equals to 1. And the knowledge of that limiting sequence is going to help you at times to predict whether the series is going to be divergent or not. Okay. Oops. What did I do? Where am I? What's happening here? Okay. Right. So here's another sequence. Again, one has to be careful again. That when you take limits, these are things that one has to watch out. Okay, if you have things like this, infinite divided by infinite, 0 divided by 0, or 0 times infinity, those numbers are not what we call indeterminate forms, so these are not really well defined. So one has to do more operation to see whether you have the sequence to be well defined or not. So let's look at this, for example. Now, if I take the limit of this sequence 2 to the power n over n squared, and n goes to infinity, what's going to happen? So here, then, no, you know that 2 to the power infinity is just infinity, n squared, infinity squared is just infinity. So you get back to this situation of infinity divided by infinity, which is indeterminate. So you need to do something else, okay? So what do we do? One of the things that we do, first of all, there's two things over here. This example are taken out in a way to demonstrate some of the tricks involved. First example, here your n doesn't appear as a power. Okay, it's not n to the something, but instead it's something to the power of n. And one is not very, if you want to do operations with things in the power, then it's a bit difficult. So what do we do in this particular case? We rewrite 2 to the power of n as e n log 2. Okay. So then I'll have over here to be e n log 2 over n squared. I'm supposed to say something else. Oh yeah, okay. This again, it doesn't help in this particular case, but you did something to get rid of this n inside this exponent. Okay, but again, this is the same thing as the earlier version. Okay, you get infinity divided by infinity. So in those particular case, we have a trick. I can't remember what it's called. I think it's Lopitas Rule. You treat this as a function of n and try to take the derivative. Okay, So this as a function of n and this as a function of n. So now I'll be able to take and the limit of that as a function of n is equal to the limit of the derivative of the function itself. Okay, so I'll now be able to do this. Okay, so this I can differentiate now. I get log 2 times en log 2, and then your n squared is just 2n. And again, we still have the problem of infinity divided by infinity when n goes to infinity in this whole thing. So you do another derivative, second order derivative. Well, I mean the derivative of the one that causing the problem, okay, the infinity case. So here you just take another derivative of exponential n log 2, and then the top, that's the top one. The bottom one is the differentiation of n with respect to n. Then it becomes 1 in this particular. And in this case, okay, no, this number is actually equals to 1. Then when you take limit n goes to infinity, your denominator doesn't go to infinity. So that's solved in part what the problem is. So all you need to be concerned is the one on top. Okay, so the one on top is going to be log 2 squared, log 2 coming from the derivative. So you have two derivatives here, so you get log 2 squared, and then you still have the 2 to the power n. Okay, and 2 to the power n, when n goes to infinity, goes to infinity. Is anyone following this, or am I talking alone? Do you have any questions? So maybe I should stop at this juncture just to see whether everything is going smooth, or do you need some break at this point, or you want me to explain explain further a few things. So this is the time for you to shout. Any questions at this point? Okay, everything is well understood, right? So you can do the exercises very well. Okay, do you want a break? Okay, we'll break for about 5 minutes, and then we'll come back. Okay. Okay. People should be coming back. That I forgot to mention at the beginning of the lecture that I'll be taking attendance. Okay, so please do stay. Those who have gone out, maybe you can ask them to come back, and then just sit in. I'll be taking the attendance right at the end of the lecture. Shall we start back? Okay. Okay. So so in this particular case, we have actually seen another what we call trick that we use to help us evaluate sequences and limits. Okay. So which is the Lopitas rule. So I'm treating your 2 to the n as a function of n, and then your n squared is another function of n. Okay. So if you've done Lopitas rule before, then you know that I can take, if I have a limiting process taken by the quotient of these two functions, then I can use the derivative. Okay, I think we'll get to that also in the power series. Okay. All right. So, oh yeah. So this is the case of this is example 1.6. What's example 1.5? I'm just recalling what I'm writing down here. Okay. There are some cautionary. No, each of these examples are taken in such a context to give you certain lessons. Okay. So here I'm not quite sure why I wrote this down, but the series is can still be divergent even if the sequence has a finite limit. Okay. So I'm not sure which example is that. I think that's example 1.4. Where is example 1.4? I can't remember now. Never mind. That is one of the lessons that one should be aware of. Okay, despite that the sequence has a finite limit, you can have the series to be divergent. Okay? So now let's go to more standard examples that we already know, which is divergence or which is convergence. One which is probably known for its divergence divergent behavior is what we call the harmonic series. This is a sum of 1 over n, where n goes from 1 to infinity. This is known to be divergent. Okay, one can go to the proof if you want, but no, I'm not. The main important thing that you learn from here, you know some standard examples of divergent series and convergent series. Okay. For the case of 1 over n squared, for example, that would be convergent. Okay, but 1 over n is going to be what we call divergent series. Now one could also have something like this. Okay, it almost looks like this harmonic series, but instead of the 1 on top, okay, maybe I should make this bigger so that it becomes clearer. So instead of just this 1 on top, I have a factor of minus 1 over on the numerator. And this so happens to be convergent, despite that the original series without the minus 1 factor is actually divergent. This one becomes convergent. Okay. So these are some of the odd things that could actually happen. And this odd thing is essentially, oops, where am I? Okay, given that this is divergent but this is convergent, then we say the second series is called conditionally convergent because it depends on this factor of minus 1 on top. Okay. And there are cases where when you take the absolute value of the series, the sequence, then you and it's convergent, then we say that the series is absolutely convergent. Okay. Example probably we'll see later on. Okay. Here, okay, I did give the proof. Okay, here is the proof of the divergence of the harmonic series. So what we do, we start to compare two different series. Okay, here, for example, I have 1/3 plus 1/4. I can say that this number is going to be greater than 1/4 plus 1/4, and then this one 1/5, 1/6, 1/7, 1/8 is going to be bigger than the sum of 1/8, 1/8, 1/8, 1/8, and you know that this sum and this sum gives you a half, and you can continue this if you want to, then you'll see that, okay, since this is bigger than that, and this is actually goes to infinity, 1 plus a half plus a half plus a half goes to infinity. So then the first series, the original series, the harmonic series, is going to be divergent. Okay. The convergence for the alternating harmonic series is given here. I think I'm going to skip that, but you can actually see, no, again, it's collecting terms, okay, collecting terms in this way and then collecting terms in this way, and you start comparing between the two. Then you find that there's a bound, and the bound is given by L here, and the same thing for the one with the other one, okay. Again, I'm not going to go for the proof. You can read it for yourself. But here you only prove it to be convergent without telling you what the value of L is. And in fact, the value of L is found out to be log 2. Okay, and this can be done through some graphical proof. Here's a graphical proof where one actually trace out a curve of y equals to 1 over x. Okay, and then you start trying to add up the rectangles inside here. Okay, and then you'll find that, okay, this essentially gives you this alternating harmonic series. Okay, so I don't want to go through this because some of this proof are not really necessary. And over here, for example, you know that you can actually convert this to this kind of proof, and then there you can actually see that it's actually equals to log 2. Okay, so this is the integral proof. Okay, here's another exercise. Since you know that your harmonic series converges to, it's not converges, sorry, it's a divergent series. Now, suppose you assume that it converges to a limit, okay? You can show that by this assumption of a limit, okay? There's a limit S over here. You can actually get a proof in such way you are proving something which is nonsensical, where S is greater than 1 plus S. Okay, so this I'll leave you as an exercise for you to do. Okay. There are other kind of series that one needs to know. Again, we have seen parts of it. Here is what we call the telescoping series, where some of these partial sums that we do starts to cancel each other. Okay, so here's an example. Sum of 2 over n squared minus 1, but you know that n squared minus 1 is a difference of 2 squares, so I can divide it by what you call, well, I mean, can factor it out by n plus 1 n minus 1. Sorry, n plus 1 n minus 1, and then you can actually write it as a difference of 2 fractions. Okay, and then here is just a relabeling. Here, if you look, you start off with n equals to 2 here, so I'm just relabeling it to so that I can get rid of this term to be 1 over n instead of 1 over n minus 1. So instead of that, then I replace it by n equals to 1. Okay. So if one writes it out term by term of this series, you get the following. You get 1 minus 1/3 plus a half minus 1/4 plus 1/3. Okay, so you can actually see this is going to cancel that. Okay, and then you have minus 1/4 here. Suddenly you have 1/4 over here. So this is going to cancel that. So you get terms cancelling each other, okay, if you write it in full. And you can essentially what you need to do is to find out the pattern, and the pattern that gives you the result in the end is that most of the terms are cancelled out apart from the first two terms, 1 plus a half here, and then the last two terms, which is a difference of 1 over n plus 1 and 1 over n plus 2. Okay, so if you start taking the limit of this, okay, because this is the partial sum, okay, so you take n goes to infinity, and what happens, this goes to 0 and this goes to 0, and then you just have 1 plus a half. So in other words, that telescoping series gives you a finite answer, so in other words, it's convergent. Okay, here is another case, almost telescoping, but you get a different result. Okay. So here you have the sum of a log n over n plus 1. And you can see that, okay, if you look at the term itself, the individual term, when n goes to infinity, no, n and n plus 1 is going to be, both going to infinity, so you get log 1 here. And essentially, you can see the limiting sequence, term in the sequence is going to be 0. Okay, but what happens is the following. The series is actually telescoping, and what one can do is just rewrite this term as a partial sum here. So you get, instead of going to go to infinity first, we write as a partial sum first. So you get log k over k plus 1, and then the behavior of log, this is log k minus log k plus 1. And then you write out the individual terms, and then you find that the cancellation of the middle terms. Okay, log 1 is of course 0, so then it doesn't give you contribution there. So the other terms just cancels out, and you're left with the last term. But the last term depends on n in this way. So when you take n goes to infinity, it goes to minus infinity in this case because of the minus sign. Okay, so despite all the properties that you think that, okay, is a decreasing sequence, and the limiting term in the sequence is 0, but yet you find that the sum is actually divergence. So the lesson that one takes from here, that telescopic series might not be convergent. So with all these different lessons to learn from looking at series, is there a better way of making the knowledge of something has a limit, or something has a divergent or a convergent? Okay, is there a more systematic way of doing things? Well, we have a series of tests that one can actually use. Okay, first is the preliminary test. So if you have this infinite series, and then the limiting term is not equal to 0, okay, then if the limiting term does not go to 0, then essentially the series almost obviously it's going to diverge. Okay, because this thing is still going to depend on this particular n. Okay, but if you have the limiting sequence, okay, the limiting sequence is going to be equal to 0, then it's inconclusive. This test is inconclusive and you need further tests. Okay. So what are the further tests that one can actually do? It's following. First is what we call the comparison test. Given that you know some standard series, you already know whether it's divergent or convergent, so we can use those knowledge of convergent series or divergent series and then make comparison with the unknown series. Okay, so here we consider, for example, that your series over here given by the symbol F, okay, is a convergent series of positive terms. Okay, and the series that you want to test is given by the symbol G. And if this G, the modulus of the terms in G, okay, the individual terms, is less than equals to the terms in F, okay, so mod Gn is less than or equals to Fn, and Fn, you know, is a part of a convergent series, then one can say that this series is going to be an absolute convergent series. Okay, so you compare it to the case with something that you already known to be convergent, okay, and the individual terms are less than the terms in the convergent series, okay, then you can actually make conclusion from there. Again, there are proofs of this, but I don't think we want to go into the proofs, and what I need you to know is essentially how to use this. Okay. Now that is for the case of a non-convergent series, and then another series compared to that. One can also use the case of a divergent series. Suppose I have this divergent series of these D's, and the series that needs to be tested is this modulus C. If this modulus C is bigger than the individual term, it's bigger than the terms in the divergent series, then definitely this series that you have over here is going to be divergent. Okay, so that's one of the thing, but this requires so-called outside help, in the sense that you need to compare it with some known convergent series or known divergent series. Another way is to look at this is, I think we have seen this before, is the integral test. Okay, so one is interested in the sum of this sequence Fn, but now you can think of it, okay, instead of taking the sum over n, you're making an integral over n, and of course the upper limit should also be infinity. Now if this integral is finite, then the sum will be converging. But if the integral and if the integral is actually infinite, then of course then this series over here will be divergent. Okay, so that's the integral test. So this is probably a little bit more helpful, but then you have to know the form of this particular function. Okay. So an example is the harmonic series. For example, earlier there was a proof which I didn't go through. Okay, but here you can use the integral test to show the divergence of the harmonic series, because now we can actually treat 1 over n as a function, okay, and integrate with respect to n, and of course that gives you log n, and log n will be taken values at infinity, and of course that gives you infinity. Okay. I think this is final one if I'm not mistaken. Well, okay, there's another one. Let me just go through. Okay, that's the last one. So another special test that's going to be very useful is the case of a ratio test. So you take terms in the sequence, Fn for example, and then you take the consecutive term and take the ratio between the two. And this ratio we write as rho n, and then see how this rho n, this ratio, okay, under the limiting process. Okay. Suppose that this under the limiting process, this is equals to rho, and you can check if rho is less than 1, then the series of this f of n is going to be convergent. If rho is greater than 1, then this series of sum of n of f of n will be divergent. But if it's in the middle, rho equals to 1, then you need some other test. So this already tells you a lot of things, because you can always take the ratios of terms in the sequence. Okay. The only problematic case is when rho equals to 1. Again, this one, the next one is a comparison test. Again, this is almost similar like the one before. So you get a convergent series of positive term, okay, and then you take the limit of you take the ratio of the convergent term with the series that you want to test. Here is given by f of n. So here's the ratio, and this ratio goes to a finite limit, but you know that Gn is a convergent series, then the sum of Fn is going to be convergence. Okay. Same thing, just like before. Here you're using the fact that you have a convergent series. You can also use the fact that you have a divergent series, and then do the same kind of ratio kind of thing. So here, in this case, you take the ratio of the tested series divided by the divergent series, and if this tends to be greater than 0, then your sum is divergent. This alternating series, you have seen it in the case of the alternating harmonic series. So what does one do is to look at the, now you have that alternating series of Fn, then what one can do is to look at the absolute values of the terms in the series. Okay, and if this satisfy this inequality, that means your consecutive term is bigger than the we call the term before that, and then the limit of Fn, n tends to infinity, is 0, then this would actually it's a bit odd. I need to check this, but I'm going to take this sentence as true at the moment. Okay, so you have to check both conditions, this condition and this condition. I'm not sure about this condition, but I'll get back to you later on to see whether this is right. Okay, so once you have that, then you will get this alternating series to be convergent. Okay, so that is some of the tests one can actually do to find the convergence or divergence of a series. So there are another few things that one can also say over here. Here is to say that the convergence or divergence of a series is not affected by term-wise multiplication by the same constant, and they are also not affected by changing just a finite number of terms. Okay, finite number of terms will not affect the whole no infinite sum kind of thing. And then two convergent series may be added term-wise or subtracted for that matter to give a resultant convergent series. So you can sum, say, Fn plus Gn, for example, where both Fn and Gn is convergent, then this series is also convergent series. Okay. And let me see what else. Terms of an absolute convergent series may be arranged without affecting the convergence of sum, but this is not true of a conditionally convergent series. You can actually see this for the case of the alternating harmonic series. Okay, so that covers part of series with numbers as the terms. Okay, I'm not sure whether I should proceed now that this is the end of lecture 1. Are there any questions at this stage? Maybe I'll just go into lecture 2 a little bit. You have the book of Boas. When you have the book of Boas, there are many exercises that you do, and probably I will set up some assignment for you to do. Probably if I have enough energy, probably weekly, or if I don't have enough energy, then probably fortnightly, so that you can actually test what you have learned. Okay, you need to test it, whether you understood or what you have learned or not. Okay, so that is a thing that you have to as a homework for your own self. If you are energetic enough, you can try to do most of the examples. At least, for example, in Boas, I think the odd numbered ones, they have answers at the back of the book. So you can easily try to do that. Okay. Of course, that doesn't mean that even numbered ones will not come out. That's a question. Okay. So you can try as much question you can try to do and see whether you can actually use all those different ratio tests or integral tests to see whether the series is convergent or not. Okay. Any questions at this stage before I proceed? Just no to begin with lecture 2. Is my lecture clear or not? How is it so far? Perhaps when you are more prepared for this, I've given the notes quite last minute because I should have given you the notes earlier so that you can actually see it. Okay, but you have the book now. You have the book. You can actually go through it. Okay. If there are no questions, let me just start off lecture 2, and then we'll try to finish at a suitable point. And then please don't run away. I will take your attendance after that. Okay. Let me go to lecture 2 then. Lecture 2 is again, hang on. Okay. Lecture 2 is again about series. Okay. Previously, if you look at the terms in the series, they are usually numbers. Okay. But now what one does is to replace those numbers by functions. Okay. And the most easy way to get a function is just to have x to the power of n, for example, over here. Okay. So this is what we call monomials. Okay. The usual one we call polynomials. Then polynomials will have many terms of x to the power something. Here's a monomial. So you can think of your fn earlier, instead of numbers, now are just monomials. And then the whole series is what we call a power series. In other words, we have something like this. You have the 0th order term a0, and then the first order term a1x. Second order term, this is wrong, this is square here, so you can do the correction yourself. a2x squared plus a3x cubed until an(n), and then of course this can go to infinity. Okay, so this is what we call a power series, because everything is determined by this power of x. Okay. Okay, just like before, you can take just like the infinite series case. Okay, you can add power series, you can add two series together. So in this way, you can add two power series together, or you can even multiply two power series together. Okay, or one of the things that we'll see later on, we can also even substitute one power series into another power series. Okay, so these two operations actually is already there in our infinite series before. Okay, where the infinite series before are just remind ourselves that they are just numbers. Okay, so we can put numbers inside another number. Well, I mean multiply rather than. Okay, so you get numbers instead of that. But now, instead of numbers, you have variables. Okay, you have variables, and that can be a bit more complicated, but all those operations are there already in the infinite series. The one that's probably not there is that now one can do things like this. One can differentiate it. A power series, it can be differentiated because it's a variable, or it can be integrated. And when you differentiate, you get another power series, or when you integrate, you get another power series. And the other thing is, this is a bit difficult for me to explain, but given a particular function, for example, later on we talk about the trigonometric function, the power series of this trigonometric function is actually unique. Okay, there's only one power series to a particular definite function. For example, the sine function or the tangent function. Okay, so they will be actually convergent to that particular trigonometric function. The only thing that's different than in the case before we talked about convergence, here because it's a variable and it's not number, one talks about the interval of convergence. You might replace your x by certain numbers and it gives you a convergent series. But if you go outside this interval of convergence, it will give you a divergent series. So in other words, one talks about, in the case of power series, one talks about the interval of convergence rather than simply convergence or divergence. Okay, so that's probably the thing different about the the previous infinite series with this power series. So let's do one technique to demonstrate how useful this idea of power series are. Okay, and then we're going to build it up to the point of defining what we call Taylor series. I believe everyone has come across Taylor series before. So here's a technique of how to do it. So you take the sine function, you assume that this is written as in terms of a power series in this way. But here you are not given what this A0, A1, A2, AN are. So you need to find out what those are. So this is not yet determined. Okay, so the problem is now to actually find what are those coefficients, okay, so that sine x can be written as a power series. So what we try to do in this particular case is to do derivatives of this power series and then take the value of x at some particular value. So in this particular case, what we want to do is to look at the derivatives at x equals 0. And once you do that, you eliminate most of the terms and then you'll be able to figure out what those coefficients are. So let's take the first case. Take the first case where you do the zeroth derivative. What does it mean by zeroth derivative? That means you don't do any derivative differentiation at all. Okay, so that means I just take your function sine x, take the value at x equals 0. What does that give you? That gives you 0, right? And you take the power series, take x equals 0. So you have all these terms going to 0 apart from the 0 or the term which is A0 that doesn't multiply x. So in other words, over here, what happens there, I'll be able to determine what A0 is, and A0 is simply equals 0. Okay, so you do the next step, take the first derivative. So the first derivative of sine x is cos x. So cos x, when you take the value at x equals 0, it's 1. Okay, and then you take the derivative of the power series. So this term goes to 0. Your a1x goes to a1, a2x squared goes to a2x, and so on and so forth. Okay, and then you take the value of x equal to at x equals 0. Okay, and this becomes 1, and this most of the terms becomes 0 apart from a1. So you get your a1 coefficient to be equals to 1. Same thing again, do the second order derivative, and you find your a2 equals 0. So I'm not going to do this in detail. And then again, the third derivative, and then you get your a3 equals to 1 over 3 factorial. And then finally, you get the famous power series expansion for sine x, which is an odd power of x. Okay, x to the power 1, x to the power 3 divided by 3 factorial, x to the power 5 by 5 factorial, or written in terms of a sum in this particular. Okay, so there, the other thing that one should also note, in the previous case, when you talk about series, you're concerned with convergence or not. Here, you know that it's going to be convergent because why? Your sine x takes values between 1 and minus 1 for all x. So in other words, this power series converge for all x. Okay. Now, can anyone see what's the assumption done over here? Can anyone guess, so that this is more a bit more interactive? What did I do? What is assumed inside in this particular technique of doing all the derivatives? when you take derivatives, uh, what is the condition for a derivative to exist? Anyone? Because no, you get bored after a while. No? 2 hour lecture is not so good thing actually. So now it's time for me to interact with you. So when you say that you can do a first order derivative, what does it mean? Say a first order derivative of function f, what is assumed about f? It doesn't have to be x not to be equal to 0 or not. Just by virtue that you say that there is a derivative. Okay, let's say a function f. I don't care what f is supposed to be, but I know that I can first take the first order derivative. So what does that tell you about f? Nobody? No guesses? No wild guess? Get your thinking cap. Something to do with e. We have not. Okay, I mean it is something to do with e, but I mean e and sine and cosine, they have a certain property, right? So if I say, let me go to the whiteboard. Okay. Now I say dx exists. Say that again. I can't really hear you. Who was the person just now? I was not seeing the. Can you say what your guess is? Right, you're almost there, but what does it mean? If I can define a slope, what does it mean? Can I define a slope for a function like this? Oh, that's okay. Maybe I should not write that. Maybe I do something like this. Can I define a slope which is this way? This is the function f. Okay. Is it possible to define what df dx for this kind of function? Let's say this is x naught. So what's the problem here? Right. Okay. So when it's not continuous, then your df dx does not exist. Okay. So if df dx exists, at least you want the function to be continuous. Okay. Similarly, for higher order derivatives, if second order derivatives exist, then your first order derivative should be continuous. Okay. So the thing that we assume in the notes before, when we are able to do all the derivatives, is to think of your sine function to be it's continuous in the original function itself, but it's also continuous in the second order the first order derivative, second order derivative, or in other words, is sometimes called that if it's continuous in all of its derivative, it's called a smooth function. Okay, so for a smooth function, you can always define your derivatives. So there is an assumption that we did when we tried to do this, all these derivatives to find your power series. So sometimes this breaks down. So you have to know when precisely you want to do this power series, where precisely where you want to describe this function as a power series. Okay, in this particular case, you must make sure the interval of x that you're looking at, the functions are smooth in that interval of x. But in this particular case, it's smooth at all values of x. But sometimes you have cases where it only becomes smooth at certain intervals. So there you know, okay, in this particular case, I'm not able to write the power series for all x, but no, I'll just look into a certain interval. Okay, so this is actually very important, and in fact, this goes to the point of the idea of Taylor series. Because the idea of Taylor series, what is it? You define your Taylor series as functions of all these derivatives. This will get to the next lecture, I suppose. Okay, so that means you are able to form all these derivatives. So in other words, Taylor series only works for smooth functions. So these are sometimes, okay, physicists often don't care about this kind of thing, but mathematicians, they do care. Okay, and if you apply the idea of Taylor series wrongly to a problem where things might be diverging in terms of the function itself, then you might get nonsensical answer. So this is where your learning of this technique of mathematical methods of power series will be useful. You probably hear some horror stories about people doing computing, for example, okay, and they simply treat the computer as a blackboard. And suddenly, when the answers that come out becomes nonsensical, it's because of these assumptions that we put into the computer program. Okay, so these are the things that you probably need to learn some of the skills to find out where a method works and where a method does not work. I think I probably want to wrap things up at that point. Probably we revisit this again, and let me take the attendance at this point. Any question, by the way? No, you have to treat things, if you're learning things, you need to be curious about certain things. Okay, so without curiosity, then no, you treat this like a history book or kind of thing. No? So then it gets boring. So let me download that. Okay, that's done. So one last final call. Any questions so far? Yes, no, or let's go home.
Yeah.
Okay, so I think yeah. Okay.
For now, I don't have any question to ask about lecture 1 and lecture 2, but after doing some exercise, maybe I will have
Yeah.
the questions.
So
Which one do you prefer to ask?
okay. Put it this way. If you have questions, you can post it up first if you want, or you can surprise me in the lecture, and I know something about it. Okay. Otherwise, I might have to think as well. Okay, I don't know everything, every single thing, so I have to look it up. Okay, so but please, no, be curious. No, you need to be curious. Your curiosity has to be very high in order to learn the subject. Okay. Okay, so I'll stop here for today and thank you. I will post up the link to the YouTube video once I process it. Okay. Okay, bye everyone.
Okay, Doctor.
Thank you, Doctor.
Okay,
Thank you,
bye.
Doctor.